So one of the things that we saw in the previous section was the fundamental theorem of calculus. And we saw two different ways of stating the fundamental theorem of calculus that are related. And this way, where you have the integral of a function, a definite integral from a to b, can be evaluated by taking the difference of an antiderivative at the endpoints. So this offers a very strong connection between integration and anti-differentiation. And you see this also in the part 1 version of the fundamental theorem of calculus, that integration and differentiation are sort of inverse operations to each other. And so because of this, one of the things that we do notationally is we actually use the integral symbol as a as notation for antiderivative. So remember, the way that we developed the meaning of this integral symbol was very numerically based, where we basically calculated this sum of terms of f of x times delta x, where delta x is this little sub-interval of the interval from a to b. And we made this sum of terms, then we took a limit as you have more and more of these terms. You divide the interval from a to b into smaller and smaller subintervals. And this is a very numerically based definition, but because of this strong relationship between integration and anti-differentiation, we introduce the integral symbol as a notation for the kind of functional definition of antiderivative. So you'll remember when we first introduced antiderivatives, we didn't have a notation for it. Every time you were asked to find the antiderivative or antiderivatives of a function, it was said in words: find the antiderivative family or the antiderivatives of this function. Okay, and so now we have this symbol, like if I just write integral of f of x dx, we are going to take this to mean the family of antiderivatives of f. So as an example, if I write the integral of 2x dx, then I know that 2x is the derivative of x squared. And it is, in fact, the derivative of x squared plus 3 and of x squared minus 7 and x squared plus any constant, because if I take the derivative of any constant, that goes to 0. So this is the family of antiderivatives of 2x. So this is a thing that we call the indefinite integral. Indefinite integral means family of antiderivatives. And if I was to integrate from 0 to, let's not say 0, from 1 to 4 of 2x dx, I would call this the definite integral. And this is where I would use the fundamental theorem of calculus part 2 to say, find any one antiderivative, capital F, and I'm going to take, so this is f of 4 minus f of 1, where capital F is any antiderivative of 2x. So we could, for example, take capital F of x equals x squared. So what we often do is we write it this way: integral from 1 to 4 of 2x dx is, I will find an antiderivative, there's x squared, and I will evaluate it from 1 to 4. So this is 4 squared minus 1 squared, which is going to be 15. Okay, and you can double check this with the geometry of the matter. Y equals 2x looks like this. It's a line with slope 2. And if I look from x equals 1 to x equals 4, you're going to have a trapezoid, and you can double check that the area of that trapezoid is going to be 15. All right, so it's important to keep straight what the indefinite integral is versus the definite integral. In the definite integral case, the result is a number. In the indefinite integral case, the result is a function. Or more precisely, it's a family of functions. Because we always have that plus a constant. All right. Now, when we talked about differentiation, we had all of these different rules of derivatives that, like, we figured out what the derivatives are of our basic functions, like our power functions and our exponential functions and our trig functions. And then we had all of these rules of, like, if you know the derivatives of these functions, here's how you find the derivatives of their sum or their product or their quotient or their function composition. Integration is different. Anti-differentiation is different. And you will see in Calc 2, there will be an entire chapter dedicated to techniques of integration. And if you kind of take a step back at each of those techniques of integration, at the very core, the way that you find the antiderivative of any function is to look at the function and go, oh, I see that this is the derivative of this other thing. So basically, the only way to find antiderivatives is to know that this is a derivative of this other function. Okay, so that is an oversimplification a little bit, but I think it is worth kind of knowing that anti-differentiation is very different from differentiation in terms of the work that you put in. Okay, and so one of the things that becomes very important is just to know a set of antiderivatives. Okay, so this is actually in the book. Right now it's on page 403 of your textbook. And all of these are basically the reverse of derivative formulas from chapter 3. Okay, so knowing what knowing what a derivative of a function is tells you something about antiderivatives. Okay, a little bit. Notice that we see that we can find the antiderivative of secant x times tangent x because we know that is the derivative of secant x. That doesn't tell us how to find the antiderivative of secant x, right? Like finding the antiderivative of secant x is going to be a harder problem. So all of these are basically memorizing these forms so that if you happen to see a secant x times tangent x show up in an integral, then you kind of, it pings some memory to go, oh, this is secant x. Okay, so I recommend that you actually memorize these in whatever way you memorize things. If you use flashcards or whatever works for you. All right, and just scrolling down, there's a couple more. There's the inverse tangent function and inverse sine function. You might notice that the inverse cosine function is missing, and that's an interesting exercise to figure out why. Also the hyperbolic trig functions, hyperbolic sine and hyperbolic cosine. We may or may not have covered this in this semester. Check with your course syllabus. Okay. So let's actually do an example of this. So in this case, we have a power function, or a sum of two power functions. And basically what we're doing here is we are finding the antiderivatives of, we can actually take the sum of two different parts. So because derivatives respect sums and differences without any fuss, antiderivatives also respect sums and differences without any fuss. So I can see this, I'm going to look at these as power functions. So this is 4x to the third power minus 5 times x to the 1/2 power. And so remember that when we take derivatives, you have a power function. We first take that power and multiply it out front, and then we drop the power. So first multiply by the power as a coefficient, then we reduce the power by 1. Reversing that process is going to be first increase the power by 1 and then divide by that new power. So the first thing I would do would be to increase this power by 1 and then divide by the power. So one of the things you can think about is you can kind of just, if your antiderivative is off by a multiple of a constant, you can just adjust by that, since multiplication by a constant is respected in both differentiation and anti-differentiation. So I know that if I got an x to the third power through differentiation, I must have started with an x to the fourth power. And you can kind of just figure out what the constant has to be. If I take the derivative of x to the fourth, it's 4 times x to the third. Oh, that is exactly what is here. And an x to the 1/2 power must have come from an x to the 3/2 power. And we've got to figure out, like, I'm just going to write that 5 here. And if I want to differentiate that, then the thing that actually happens is the first thing I'm going to do is I'm going to multiply by 3/2. So I want to undo that by multiplying by 2/3, or which is the same as dividing by 3/2. And I'm just now realizing I accidentally wrote this integral symbol. It's no longer there. Okay, so double check that when I differentiate this term, the first thing I'm going to do is multiply by 3/2, which is going to cancel out with that 2/3. And then I'm going to reduce the power by 1, which is going to give it to 1/2. Okay, so the last bit is to add a constant. And now I'm going to clean this up. So this is x to the 4th minus 10/3 times x to the 3/2 plus a constant. Okay, and so what we get is the antiderivative of 4x to the 3rd minus 5 square root of x dx is x to the 4th minus 10/3 x to the 3/2 plus a constant. And we can check this by differentiating. So if I take the derivative of x to the 4th minus 10/3 x to the 3/2, this is, sorry, plus a constant. The first term is going to be 4x to the 3rd power. And then we have 10/3 times 3/2 times x to the 1/2 power, and then plus 0 when we differentiate that constant. So this is 4x to the 3rd minus those 3's cancel, and I have 10 divided by 2, which is 5. 5, and x to the 1/2 is the square root of x, which is exactly our integrand.